And so much for the introduction. It's time to dig in to a deeper part. I am Errol Ann Picenteno and I'm going to present to you the general design procedure for a gas absorption system. There are different factors to consider in the general design procedure. Of course, we are required to determine the best solvent to use for the system. And then we also have the best gas velocity through the absorber, namely the vessel diameter. We should also determine the height of the vessel and its internal members, which is actually the height and type of packing or the number of contacting trays. One should also determine the optimum solvent circulation through the absorber and stripper. Then, we should also know the temperatures of streams entering and leaving the absorber and the quantity of heat to be removed to account for heat of solutions and other thermal effects. We should also determine the pressures at which the absorber and stripper will operate. And lastly, we need to know the mechanical design of the absorption and stripping vessels. This actually includes the columns or towers, plus the flow distributors, packing supports, and so on. Before we discuss those factors in details, now here are some of the quantities that are usually specified in problems presented to the designer of a gas absorption unit. First, we have the gas flow rate. Then, we have the gas composition, which is at least with respect to the component or components to be absorbed. The operating pressure and allowable pressure drop across the absorber. Then, the minimum degree of recovery of one or more solutes and, possibly, the solvent to be employed. However, the operating pressure, the minimum degree of recovery, and the solvent to be employed is actually subject to economic considerations and therefore are sometimes left up to the designer. Okay, so it's time to go back to the factors that we have discussed earlier for the general design procedure of a gas absorption unit. First off, we have the solvent. For the selection of solvent, actually, liquids with high solubilities for the solute is preferred. Why? Because a high solubility reduces the amount of solvent which is needed to be circulated in the whole unit. This makes it more efficient and of course less costly. And here are other characteristics of the solvent that one should consider. The solvent should be relatively non-volatile, inexpensive, non-corrosive, stable, non-viscous, non-foaming, and preferably non-flammable. In addition to that, since the exit gas normally leaves saturated with the solvent, solvent loss can be costly and may present environmental contaminations problems. And for that, low-cost solvents may be chosen over more expensive ones of higher solubility or lower volatility. Solubility values actually play an essential role in the design because it determines the liquid rate necessary for complete or economic solute recovery. And for us to define completely the solubility of a gas in a liquid, it generally is necessary to state the temperature, the equilibrium partial pressure of the solute gas in the gas phase, and the concentration of the solute gas in the liquid phase. And now we've come to another important part of the gas absorption unit, the equipment. And for the selection of type of packing to be used, one should consider its resistance to corrosion, the mechanical strength of the material, its capacity for handling the required flows, mass transfer efficiency, and of course, the cost. There are usually two types of columns that we use for gas absorption unit. We have the packed columns and the plate columns. Let us consider the packed column first. Packed columns are chosen for very corrosive materials, for liquids that foam badly, for either small or large diameter towers involving very low allowable pressure drops, and of course for small-scale operations requiring diameters of less than 0.6 meters or 2 feet. While the plate columns may be economically preferable for large-scale operations. And plate columns are actually needed when liquid rates are so low that packing would be inadequately wetted. Also, plate columns are used when gas velocity is so low. Lastly, plate columns are used when intermediate cooling is desired. Now, moving on to another important part of the factors to be considered in the general design procedure of a gas absorption unit, we now have the pressure drop. And for the maximum allowable pressure drop, it actually depends on how much energy was used for the compression of the feed gas. Next, let us consider the column diameter. For the column diameter, the minimum possible diameter of the absorber column is determined by the flooding. And usually, the design is for 60 to 80% of the flooding velocity. Lastly, we need to consider the computations of the tower height. For the required height of a gas absorption or stripping tower, it actually depends on three things. First is the phase equilibria involved, then we have the specified degree of removal of the solute from the gas, and lastly, the mass transfer efficiency of the apparatus. Now, these considerations actually apply to both the plate tower and the pack tower. While the theoretical stages for the plate tower and the number of transfer units for the pack tower actually depend on the phase equilibria involved and the specified degree of removal of the solute from the gas. And in addition to that, the mass transfer efficiency of the apparatus is derived from the tray efficiency and spacing for the plate tower and from the height of one transfer unit for the pack towers. The solute removal specifications normally are derived from economic considerations. And that's it for the general design procedure of a gas absorption unit. Let us now have Ms. Claudette Ann Capilli to discuss a sample problem for the design of the gas absorption unit.